Thanks for the introduction, and thanks to all of you for joining our sessions today. I will be happy to stay after for follow-up questions. We also have a booth in the Designer Expo with additional information and demos. My co-author, Andy Espenscheid, was not able to attend Cadence Live this year. To be honest, the credit for this presentation goes to Andy and the IC Managed technical team. Let's start with the definition of the main topic for today. What is an IP catalog? At the most basic level, it's a place to store IP design data so that it can be found and used for multiple SoC projects and tracked throughout its lifecycle. What do we mean by IP to be organized? Of course, we want to organize internally developed, synthesizable, and custom design information, but for completeness, it should also include verification, external IP generators, and firmware so that later users of IP have a complete and accurate picture without needing to track down missing data or information about how the IP was built. As you can imagine, with a very long and successful history of developing unique products to a wide range of end-user applications, NXP has a lot of IP, correspondingly a lot of business units delivering solutions to very competitive markets. NXP is a global design team with thousands of engineers, so any solution to this problem needs to be easy to use and maintain performance across multiple continents. One of NXP's advantages in the market is that it has access to a wide range of silicon technologies that can be leveraged to deliver unique solutions. A wide variety of similar IP targeting different technologies means that any IP catalog needs to provide navigation and search options to identify which of many options will be the best fit for a new project. Over its 50-year history, NXP has deployed many enterprise systems to support design and manufacturing activities. Deploying an IP catalog needs to augment these systems and be able to interchange information with them as well, to present users with a complete view of their IP usage and characteristics. Two examples of very important existing systems in use are the Product Lifecycle or PLM system that stores the actual IP design data, and a tape-out management system that collects information about which products have been sent for production. So where did the need for an IP catalog project start? First, the PLM, data management, and tape-out management systems in place were effective in helping design teams complete projects. The PLM system had information about tens of thousands of IP parts, but had no designation on if they were reusable or how to reuse them. Engineers really had to track down the original IP owner to find out basic information to decide on which IPs they might want to use. What that meant was that NXP needed a formalized method to identify which IPs were reusable and have a consistent organization of metadata so that IP could be categorized and searchable. At the end of the day, NXP needed a faster way to find reusable IP so that project managers and integrators could be more efficient and confident that they were using the best IP for the product they were developing. There were two major desired outcomes. First, to make it so that IP producers had a clear and streamlined method to publish analog and digital IP. This is possibly the most important factor in deploying an IP catalog, minimizing the overhead of the IP creator so that it doesn't impact their productivity. The second desired outcome was to make it easy for the IP consumers to find the best IP from thousands of options. The goal was to emulate the usage model of a modern electronic component catalog like DigiKey that is popular in the United States. This helps to minimize training and ensure robust search and filtering to find the right IP quickly. So all this doesn't just magically happen. Let's talk about some of the key technical challenges. The advantage of many mature companies like NXP is that they have systems in place to ensure correctness and quality. The downside is that some of these systems weren't architected to support web applications and extensive load created by thousands of live users querying tens of thousands of components with hundreds of metadata fields. IP search functionality is obviously key to finding reusable IP. However, different types of IP need different metadata fields. Think about analog technology nodes versus digital functional coverage. This means IP datasheet pages will be a mix of common fields like owner, but also different fields for dozens of different categories of IP. This also means that search pages would need to have different default search fields for each IP category, and users would want to customize the search results for themselves. The next challenge is how to keep the IP catalog up to date with changing information in other systems. It's important in a system like this not to have multiple sources of the same data, which will get out of date quickly. Based on that, the IP catalog would need to pull in updated metadata fields from the PLM and tape-out systems frequently, so that search results are always up to date. This needs to happen multiple times per day. For end users to find the system valuable, it would need to be easy to find and determine which IP would be the best fit. That implies having a robust set of metadata in an IP datasheet that answers all the key questions an IP consumer would have. Things like quality levels, whether it's been verified in silicon, known bugs, links to release notes, all in one place. So let's move on to implementation challenges. An easy-to-use web UI is the minimum requirement. Search can take on different flavors. There's that Google-like search that says, here's a set of keywords, find any matches. Of course, when we want better refinement, we want a search that gives us some standard filters like technology node, IP name, quality, or maturity. So that's of course easy to describe, but organizational alignment on the essential set of metadata to control the publishing and search elements needs to have consensus across the producer and consumer populations. This is not really a technical issue, but user input is the key to gaining acceptance and eventually deployment. It really needs to be obvious to the producer and consumer where the IP is at as it is prepared for publishing, and equally important for management to trace reuse so that they can identify high-impact IPs and have a starting point to understand IP that is not being reused. A common data model for each category needs initial definition. Of course, it can and should change over time, but with many business units and engineering roles working on IP, the data model needs to make sense and accommodate different end user needs. And of course, having reliable, maintainable, and adaptable connections to existing data sources. For a successful deployment, NXP's Andy Espenscheid had a process of getting consensus that was at least as important as the technical features of the underlying product. Andy was extremely effective in defining a strategy and executing it so that the IP catalog could be deployed. The first step was to define the business goals and get senior and line management buy-in. Second important topic is communicate. Andy conducted a multi-day workshop to get initial input from users and managers. This was followed by defining a robust spec and use cases that were reviewed by the key stakeholders. This is when technical development with specific targets started with IC Manage. Once a prototype IP catalog was built to the spec, user acceptance testing would be needed, so that user feedback for the end product would be implemented before going live. The key success factors were making sure that search results and page loads came back quickly, and users were able to navigate the system and take IPs from newly loaded to published and ready for reuse. To ensure consistency with the system's data loading was not a one-time exercise, but it needed to be frequent, robust, and prevent any data errors from propagating into the IP catalog. The next stage of the project was to establish a collaboration workflow. NXP and IC Manage decided that the most optimal development path was to establish development and test servers at NXP and give IC Manage R&D direct access to them. This enabled very fast turnaround for new NXP requests or bug fixes during the development phase. To ensure adaptability and reduce software update schedules, the IP catalog metadata schema can be directly modified by the end customer. In this case, NXP can edit simple JSON files and upload them to their IP catalog server to add, modify, or remove metadata fields. This eliminates a long feedback loop to IC Manage that would be required to create new software releases for simple database changes. We also had the benefit of very fast feedback from NXP's development milestones, which significantly reduced the traditional product development lifecycle. 2 user acceptance test phases were scheduled prior to full deployment. This was important to make sure performance, functionality, and quality goals were met. Now, what did IC Manage bring to the project? First off, we enhanced our global design platform, which used an SQL database, to a graph database with our GDPXL platform. This GDPXL platform outperforms SQL-based implementations by at least a factor of 10 and sometimes 100x. For application developers, a 5x improvement in productivity has been reported. For end users, most search and IP data sheet pages load in less than a second. Extremely important is that GDPXL provides a metadata schema that can be customized for every IP category, or even every IP. And the end customer can modify the schema as required. This means the platform can adapt as often as needed and not require new user software builds or costly server upgrade cycles. The schema is defined in a text JSON file that can be modified and uploaded to the server. And the schema can be verified against the existing data on the server to ensure that there are no incompatibilities. This enables new UI updates for search pages and IP datasheets with no code changes. On top of the flexible database schema, IC Manage provides a number of workflow automation utilities and an API to update metadata from external systems multiple times per day. Our 20 years of working with most of the leading semiconductor companies has resulted in domain expertise as well as highly scalable solutions. Now let's get into some additional IC Manage detail. This diagram shows the IP catalog server architecture, which has a number of embedded services and interfaces to external systems. On the left side, NXP's PLM and identity management systems have live data access connections. On the right side are user interactions, web pages for search and IP datasheets, and report pages. On the bottom, links to external documentation systems and software repositories that are embedded in the IP datasheets as well. The first navigation option is via functional classification. All IPs are associated with a functional classification category, and you can see these have multiple subcategories for easy browsing. These are user-definable and maintainable, so these categories can grow easily over time. This page shows a sample IP datasheet that is generated for every IP. Note that this is not an NXP IP datasheet, but an example of the types of fields that are representative for an IP category. The metadata properties are divided into groups, and every IP category can have its own set of common or unique groups of metadata. The underlying fields can be defined to be strings, single or multi-select lists, numbers, etc. Updating the IP lifecycle state can also have required fields to be completed for an IP to be published and reusable. As with the datasheet, each IP category in the functional classification hierarchy can have its own search page. This search page is an example of an analog IP. Note that the tech nodes have been grayed out on the left side of the window to protect NXP confidential information. The user can see all results or select the relevant fields before searching, or use the filter windows after the search has completed. A user can also change the result columns if needed, or export to a CSV file if desired. Let's take a look at the IP lifecycle state diagram. As part of the IP catalog workshops at NXP, the team agreed on a specific set of IP states to enable IP developers and their managers to keep track of IP as it moves towards being published or reusable. The IP catalog search utilities can filter out search results for IP consumers so that they only see IP that is published. At the same time, IP producers for a given category can see all the IP in any state for that category. As we noted in the GDPXL system architecture, it is possible to embed HTML links to other services, like documentation systems or verification trackers, so that the user has a single IP window, which pulls in all relevant information together. So what has NXP accomplished so far? First, the IP catalog is now the rallying point where IP developers and product teams come together. NXP management uses the system to prioritize IP reuse efforts so that they can measure how effective their strategy is delivering IP development cost reduction. As a side effect of deploying the IP catalog, new IP was discovered during development and user acceptance testing. This IP turned out to be of significant interest and was not previously known about. End user and management feedback confirmed that the performance and usage model defined during the workshop and verified during the user acceptance testing phases was delivered with a positive outcome. The NXP team now has a platform that links together all key design systems and streamlines adding IP to the IP catalog. NXP is also able to adjust their own data model as needed without requesting product updates from IC Manage. This contrasts with typical PLM systems that require custom database programming and challenging software version upgrade validation. And the IP catalog is the key to improving return on investment from IP reuse. So let's recap. An effective IP catalog requires flexible IP data and metadata models, tight automated integration to design and verification flows, consistency to enable IP to be found and reused, and a secure, high-performance infrastructure to minimize overhead and prevent IP theft.